Hi dear students, welcome to Wallah. So this is Satish Kumar Dirshetty, Faculty of Measurements and Instrumentation, and welcome to the one-shot series on the measurements. In the next lecture, we are starting here with the measurement of power. In the previous lectures, we have discussed the PMMC and moving iron, and in today's class, we are going to cover the measurement of power. Of course, in the previous classes, we have elaborately discussed what is PMMC, what is moving iron, and how they work, and their range extension, and the previous year gate problems extensively we have discussed. In today's lecture, we have to talk about the measurement of power, but before that, we have to talk about the dynamometer first. So, these are the contents for today. In this lecture, I am going to cover electrodynamometer constructional features and what is the 2-watt meter, and next the 3-phase power measurement by using the 2-watt meter and numerical problems related to the 2-watt meter and measurement of power. So directly we will start the dynamometer constructional features. Before starting the dynamometer, first let me write about some points about the PMMC. What is PMMC? PMMC stands for permanent magnet. Yes or not? So there is a permanent magnet and there is a moving coil. There is a permanent magnet and there is a moving coil. Got it? So this is a permanent magnet and moving coil. Second, it is suitable only for DC. Next comes the moving iron instrument. Moving iron instrument, we are having the electromagnet. We are having the electromagnet. But in the place of moving coil, we are having the moving iron disc. Moving coil is not present, moving iron disc is present. And the important point, it is DC as well as AC measurements. Now, dynamometer. What is a dynamometer? Dynamometer will take the feature of electromagnet from the moving iron instrument and will take the feature of moving coil from the instrument. So all together, so the dynamometer is a combination of dynamometer is a combination of electromagnet, and moving coil. Electromagnet and moving coil. That's why in short we can say it can be called as EMMC. What we can call this as EMMC, electromagnet moving coil. Okay, so by using this EMMC, we can measure the current. Dynamometer can be suitable. Dynamometer is suitable as dynamometer type ammeter, and dynamometer type voltmeter, and most importantly dynamometer type wattmeter. Dynamometer type wattmeter. So here the deflection is proportional to I square, and here the deflection is proportional to V square. Okay, now this is proportional to I square, and whereas this is proportional to V square, and here comes why it is called wattmeter. It is proportional to the average power. So dynamometer is a transfer type instrument. You may be having a doubt, sir, by using PMMC, by using moving iron, why can't we measure the power? Yes, obviously, for example, if you use the PMMC, it can be suitable for DC current measurement and DC voltage measurement. So one ammeter in series and one voltmeter is across the load. We can measure the V and I. So the product of both is equal to V into I. Similarly, if we want to measure the AC power, I can use the moving iron instrument as an ammeter and moving iron instrument as a voltmeter. One can be connected in series and other can be connected parallel across the load. I can measure the power by using the V into I. But the problem is to measure one single parameter called power when you are using the multiple meters. As you know, each and every meter is suffering with error. PMMC is suffering with frictional error. moving iron is suffering with frequency error. So definitely these errors are going to be more. More is the number of instruments for measurement of one parameter, more errors are possible. That's why exclusively for power measurement we are using a single meter, but it takes certain features like electromagnet from moving iron instrument and moving coil from PMMC. Together the dynamometer is also called as electromagnet moving coil instrument. What we call it as? We call it as electromagnet moving coil type instrument. Now let us see the diagrammatical feature. So just I have taken a rough diagram here. Board. So the fundamental thing here is the dynamometer contains two current coils. These are called current coil, so which is fixed. So this is a fixed coil 1 and this is the fixed coil 2. The fixed coil is used to carry the current. So that's why their constructional features are accordingly. And whereas this is the moving coil. So here we are having the moving coil. How it acts, I will tell you. So if you see this particular fixed coils, the fixed coils are thin. Let me take this diagram. So what is the diagram? Yeah. The dynamometer majorly contains, let me write some points first. The dynamometer majorly contains fixed coil and moving coil. Fixed coil and moving coil. That's why it is what we call as electromagnet. When the current travels into the coil itself will act like a magnet. This fixed coil is also called as current coil. In short, we call it as CC. Whereas moving coil is also called as potential coil, or in short we call it as PC. Is also called as pressure coil, or it is also called as voltage coil. So this current coil is used to develop the current ICC, and this potential coil is used to measure the current IPC. Potential coil purpose is to measure potential C. The product of these two will give you the power. But the features of fixed coil are, the fixed coil has to allow the current. That's why the fixed coil is thick in size, shorter in length. So this is the fixed coil feature. The major feature of the fixed coil is thick size. Second feature is short length. Why, sir? Thick. When it is thick, what happens? Diameter is more. The diameter. So for a second, take, for example, if you take this particular thing like this, more thick in size, take like this. So this is what we call as diameter. Okay, so that is a diameter. So when diameter is more, area of cross section is more. When area of cross section is more, the resistance, according to formula, R is equal to rho L by A. R is equal to rho L by A. When area is more, resistance is less. When resistance is less, the current passing through that particular coil will be more. So that's why the fixed coil is called as current coil, because its constructional feature is such a way it will allow the current through it by having its diametrical cross-sectional interface, cross-sectional area is more, its thick in size, diameter is more. When diameter is more, resistance is less, it allows more current. But whereas the moving coil is thin type and or narrow type and longer length, longer. So these are the features of moving coil. Okay, so fixed coil features you understood, and the moving coil. Why the moving coil? When length is more, its resistance will be more. When resistance offered is more, the potential can be developed easily. Okay, so the more time it takes the current to travel in the resistance, so it is the features of the moving coil. Now keeping this in mind, let me draw the diagram of the dynamometer. So dynamometer contains current coil, but the current coil is split into two parts. Actually, it is a single current coil, but it is split into two parts like this. The current coil is split into two parts. The load okay. So now just imagine here. Let me explain the diagrammatical feature, because constructional features, if you understand, automatically the derivation part you can understand. So whenever the current travels here, so as I told you, whenever the current travels here, now this is the fixed coil and this is the fixed coil. The current passing through the current coil ICC, so the direction of the current. So this is the direction of the current. Okay, so this is how the current goes, and this is the same current which enters into the load. Now whenever the current enters into these fixed coils, what happens? As per the concept of electromagnet, when the current enters, these particular coils will become like a magnet. So there is going to be a magnetic bar like this. So this is a north pole you can take. It acts like a magnet and it also acts like a magnet. Okay dear. So these two are going to act like a magnetic bar. Don't confuse. Just I am using, for understanding purpose, I am using a magnetic bar. It acts like a magnetic bar. It also acts like a bar. So if you take this as a north pole and if you take this as a pole, the north pole and this is understood. So between the two magnets, now here comes our moving coil. So here there is a moving coil. So this is our moving coil. Got it? So now this particular moving coil is narrow in size. Okay, the coil like this. Now what happens if you see the current direction? The current which is traveling here, there is a current coil, and the current whichever is coming here, the direction of the current is like this. So then definitely what happens? There is going to be a reverse magnetic field. Okay, the direction of the current is different here. So then definitely what happens? There is a repulsion between this north and south. So now slowly what happens? This particular moving coil experiences a deflection. The reason behind it is when the same series current travels here, but the directionally there is an opposite. So there is another magnetic field is going to be created in that magnetic coil, because they are all electromagnetic coils. So that is the advantage of this particular dynamometer instrument. In dynamometer instruments, we are having 3 coils, but the 3 coils are lightweight because they are air cored coils. So these air cored coils will have certain magnetic flux opposite to each other, so which is having a reverse magnetic field, so which makes this particular moving coil to deflect. Okay, so whenever it makes a deflection, what happens in this diagram? This particular moving coil deflects like this. So this particular moving coil may be deflecting like. So it deflects like this. So whenever there is a deflection like this, now what I will do, I will attach a pointer for it. I will attach a pointer for it, and this pointer, okay, so this pointer, what it is going to do? This pointer is over a deflection here. Pointer is going to give a deflection. So here the important point is the current passing through the fixed coils. The 2 fixed coils are measuring the current, and the potential coil which is here, it is going to give the voltage. Okay, so now if you want to take the relation between these, we can express the deflection torque and the controlling torque. Okay, so the deflection torque and the controlling torque expression I will discuss, but before that, what you have to understand here is the most important concept. For the positive half cycle, there is a deflection, I agree. When the positive half cycle, that means AC current travels, this particular magnetic fields are north pole, south pole, north pole, south pole, and internally this particular moving coil is having some reversal effect, so there is a deflection. But what happens whenever there is a polarity change? When polarity change, here also south north will come, here also north south will come, and definitely what happens, the particular deflection will continue, because the magnetic flux is there, and the between the current coil and the moving coil, the deflection continues. So that is the reason why the dynamometer type instrument is best suitable for both AC as well as DC. It will work both as well as AC and DC. Okay, but we have to do some arrangements to this particular diagram to make it to effective measurement of the power. Okay, so that we'll go through now, first by taking an expression of deflection torque and the controlling torque. Now we'll move for the measurement of deflection torque and controlling torque. So for the understanding, I have taken this as I1 current and this is the I2 current. Okay, so basically the deflection torque is given by the expression. So I'm taking directly the torque expression because we are not deriving the torque expressions. So this is the I1, I2. Okay, so it is related to the terms current I1 term and I2 term into dm by dt term, because dynamometer is such an instrument which works according to the concept of not self-inductance, it works according to the concept of the mutual inductance. So this is the dynamometer deflection torque expression. Please make a note of this point. This topic is related to what? This is deflection torque. So this is the deflection torque. Deflection torque. Now from this, If you take these two currents are equal in magnitude, so dynamometer type ammeter, for dynamometer type ammeter, what will happen? So this will be deflection torque will be equal to I square to dm by dt. Take two currents are equal. Okay, and what is the controlling torque? The controlling torque is always same expression, Tc is equal to Kc theta, where Kc represents the spring constant and theta is the deflection. Now at steady state what happens? The deflection torque and controlling torque both will be equal. So deflection torque and controlling torque both are equal. So we can write this I square dm by d theta is equal to Kc theta. So from this we can write theta is equal to I square by Kc into dm by d theta. That means we are going to have a relation of theta is proportional to I square. Okay, so this is dynamometer type ammeter. Now if we go through the dynamometer type voltmeter, what is going to happen? If we go to the dynamometer type voltmeter, what is going to happen? Take we go to the dynamometer type voltmeter. So instead of taking this, so if you take the dynamometer type voltmeter, what is going to happen? If I take this current I2 as a current passing through the pressure coil, so if you take the deflection torque is equal to I1 into I2 into by d theta. So this is a current passing through the current coil and this is a current passing through the potential coil and dm by d theta. Okay, so now what I can write here? This ICC, IPC both I can express, yes or not, in terms of the V square. That means I can write this also voltage. Okay, so voltage by R and this also voltage by R dm by. So I can write this expression as V square 1 by R dm by theta. Okay, and what is the controlling torque expression? Tc is equal to Kc into theta. So at steady state what happens? At steady state when you write this one, V square by R into, okay, so this is the resistance of the pressure coil, we can write. Second. Yeah, this you can take the V by total resistance. You can take the total resistance of the circuit. So V square by R square into dm by d theta equal to total circuit, that is equal to Kc theta. So theta is proportional to V square. So it acts like dynamometer type voltmeter. So what we can call this as, this acts like dynamometer type voltmeter. This acts like dynamometer type voltmeter. Understood? This acts like dynamometer type voltmeter. So now the most important thing is I want to convert that into dynamometer type wattmeter. So to convert that into wattmeter, so what I am taking here, the deflection torque is equal to I1 into I2 into dm by d theta. If you take I1 as some Im1 sine omega t, definitely I2 will be having some difference phase, I2 sine omega t minus phi, because both are directionally different. Okay, both are directionally different. So now what is going to happen to the deflection torque? the deflection torque I can write it as Im1 into sine omega t. This is Im2 into sine omega t minus phi into dm by dt. So as we know, it measures the average. So what is the average? How to find out the average? So the average torque that we can take it as 1 by t integration of 0 to 2 pi the td into, yes or not? So here, so this is, sorry, d omega t. You can write it as d omega. Why? Because theta is equal to omega t here. So now what I can write, this is 1 by t means 1 by 2 pi. Okay, so this is 1 by 2 pi average torque. So 0 to 2 pi, the deflection torque I can write it as Im1 sine omega t into Im2 sine omega t minus phi dm by d theta into d of omega t. Okay, this will be taken as this one, I can take it as of omega. Okay, so what I can write here now, I can take this Im1 Im2 dm by d theta out 1 by 2 pi. Why? Because average torque, we are going to measure the average torque. So 1 by 2 pi. So this one I can take it as 0 to 2 pi sine of omega t minus phi. Okay na? Sine of omega t into sine of omega t minus phi to d of omega. Okay, so further simplification, if you do and make some mathematical integration, what I am going to get here is, I am going to get the final expression as Im1 into Im2 by 2 cos phi dm by d theta. I am going to get. So what I am going to get, the deflection torque expression I am going to get as Im1 into Im2 by 2 cos phi dm by d theta we are going to get. This is the expression, most important expression you have to understand with respect to the dynamometer. The mathematics part you can go through, integration you can do it. So this one I can write like this. This is Im1 by root 2 I can write. This is Im2 by root 2 I can write it. And this is cos phi into dm by d I can write. Okay. So this is the average torque. What we call this as, this is the average torque. So now if you take this Im1 by root 2 as RMS, so let us take this as RMS. So this is I1 RMS value and this is I2 RMS value into cos phi into dm by d. So here the point here is, if you compare this expression of average torque, generally what is the power expression? So before that we will take Tc is equal to Kc into theta. Power means what? Power means Vi cos phi, yes or not? So Vi cos phi should come and this dm by deta term should not be there. So for that small adjustment. So now if we take it steady state, what happened? This I1 I2 cos phi dm by d theta must be equal to Kc theta. So from this, if I am sending the Kc here, so this theta will be equal to I1 I2 cos phi 1 by Kc dm by d theta. These expressions may not be looking good for you, but they are important in understanding the things. So this is a current passing through the current coil. I can write ICC. This one I can write as VPC by R. So now this expression of the theta is going to become how much? Take this theta. So this is the I. So this one I can write I is equal to V by R cos phi into 1 by Kc dm by. So if you send this R to this side, what I am going to get? Theta is equal to Vi cos phi 1 by R 1 by Kc dm by d theta. So which is nothing but the deflection is proportional to the average power. Vi cos phi is what? Vi cos phi is the average power. Okay, so this is the expression you have to remember. But for this, small adjustment has to be done. Otherwise, how this particular voltage will come here? So to get the voltage across particular that potential coil, we have to attach a. Okay, so how to do that? So for that, I want to make a connection here. Okay, so what I am going to do, listen carefully. I am taking the current coil, and this another current coil, and this our load coming here. Okay, and here comes our potential coil. Okay, so before that, so let me take this the current coil. So this is another current coil, and here I am taking the, what do you say, spindle. Okay, load. So on the spindle I am taking the moving coil like this coil. Okay, small adjustment we have to do to get the voltage, because the deflection torque is proportional to average power, that the theta is proportional to average power. So how to get this V? So to get that V, what I am going to do, this is a moving coil, my dear, taking this as a moving coil. So here we are having two springs. We can take one spring here, and this is another spring. Okay, so these are the two springs. So to get the potential voltage, so this is our load. Now observe carefully. So this is the current passing through the current coil. So this is a current coil, the current coil. Okay, so now how to get the voltage? To get the voltage, what I am doing, some adjustment here. We are going to attach, this is a moving coil, definitely. Why? Because the controlling torque is provided with the spring. Whether it is a PMMC, moving iron, or dynamometer, the controlling torque is always produced by the springs. But the thing here is how to get the potential coil voltage. So for that, I am going to attach one series resistance. Okay, in series to the spring, I am going to attach one series resistance. So that particular series resistance is going to be a pure resistive, non-inductive resistance. So that it can develop some voltage, and the deflection, that whatever that you are getting here. So this deflection, my dear. So this deflection is as a function of power. Thus, theta is proportional to I square. Okay, theta is proportional to I square, but theta is proportional to average power. Just be, the theta is proportional to this average power. If you observe this diagram, so what is this? Theta is proportional to Vi cos phi. So theta is proportional to average power. How that linear relationship comes? Of course, this particular spindle is in a part of say is a part of our as the balls are very, because I want to show you the perfect diagram, my dear. Then only up we get the clarity. Ball bearings. Okay. So now in series, I am attaching a series resistor. What is this? I am attaching a series resistor, so that across this moving coil you are going to get a voltage. So this is our single phase AC supply. I am going to get the voltage here. Okay. So we are going to get a voltage experiencing here, so which is nothing but voltage across the pressure coil. So that is the reason why, if you see, for dynamometer type, have you seen this diagram clearly now? We have done an adjustment. We have done an adjustment by connecting a non-inductive pure resistance in series with a moving coil. A voltage can be developed. That is a point you have to understand. By connecting a non-inductive pure resistance, please make a note it off. By connecting a non-inductive pure resistance, we can make it off like a dynamometer type wattmeter. Now this diagram will become like dynamometer type watt. Until you don't connect this particular series resistance, you cannot develop that expression for the dynamometer wattmeter. Thus, this particular thing now gives you theta is proportional to Pi cos phi, dear. Okay. So once again I want to tell you here. Dynamometer type voltmeter we have seen. Dynamometer type ammeter we have seen. Dynamometer ammeter theta is proportional to I square expression, we got it. And dynamometer voltmeter theta is proportional to V square expression, we got it. But when it comes to the dynamometer type wattmeter, that expression is theta is proportional to I cos phi. So that's the reason why how to draw the diagram. So how to draw the diagram? So the better way to represent the diagram here is, in textbook pictures we won't see multiple coils, we'll see only one current coil. So this is our load. Okay, now next comes the potential coil. Our potential coil, and potential coil is having a call as, and this connection makes most important point here. This connection is the most important point. Either I can keep here or here. Okay. So now this is the best view of the wattmeter. The wattmeter is red. Wattmeter is red. Okay. This is the best view of the. So this is our current coil. Our potential coil. So this is the AC supply. Okay. So now we can write the deflection torque, whatever you are writing, the deflection torque expression is what? I1, I2 proportional. Yes or no? Deflection torque is proportional to I1, I2. Whatever that you have taken, previous expression. What is the expression for TD? We got it. Previous expression. TD is equal to I1, I2 cos phi dm by dt, right? So now comfortably you can write. So this is I1, I2 cos phi dm by. So I can comfortably write now deflection torque is a current passing through current coil. I2 means current passing through the potential coil. Cos phi to dm by dt. And all of you following, why it is suitable for the average power. So this is a proof. So deflection torque I can write, this is the ICC and this is the VPC by R series resistor. Okay na, to cos phi dm by Okay, so this is the deflection torque here. So now if I keep this deflection torque in brackets, next comes the controlling torque. Controlling torque is equal to theta. So this is the controlling torque we are going to get. So now at steady state, what I am going to get, TD is equal to TC. If you check it, ICC EPC by R series cos phi dm by theta is equal to AC into theta. So theta is equal to ICC EPC cos phi to 1 by RSE series resistor 1 by AC dm by theta. I am going. So this is now nothing but, if you take this whole as constant, so theta is proportional to EPC ICC cos phi. One of the important bit, theta is proportional to average power. Theta is proportional to average power. That means if you draw the scale, you are going to get the scale as linear. If you draw the scale is going to be linear. So dynamometer type ammeter, if you check, dynamometer ammeter, if you check the scale, the theta, sorry, dynamometer ammeter, the deflection theta is proportional to I square. So if you draw the scale, the scale is like this. Theta is proportional to I square. We are going to get a non-uniform scale. Non-uniform. The I and this. Next, if you take the dynamometer type, voltmeter, this. So this is the V and this is the theta. Theta is proportional to square. The scale is again non-uniform. But when you take the scale of dynamometer wattmeter, the theta is proportional to the average power, VI cos phi. So if you draw the scale, the scale is going to become perfect here. Scale is perfectly linear. So that's why dynamometer is best suitable for power measurement. The readings are reliable. So dynamometer best reliable for average power. That is the conclusion. So that is the test. Is it visible, audible? Okay. So I have given you in this particular session segment dynamometer type ammeter, dynamometer type voltmeter, dynamometer type wattmeter. Okay. So now let us move to the next important point, error due to the pressure coil connection. So as I told you in this picture, the pressure coil can be connected at the front of the current coil or at the back of the current coil. Based upon the connection, we are going to get some error. How? Let us see. So error due to pressure coil connection. How it is possible, sir? So let me take the current coil. So this is the current coil. This is connected to our load. And here comes potential coil. Let me take the potential coil like this. And the potential coil is connected to the current coil, potential coil. The connection is here. So if you take supply, the load, now what happens? Let us observe. Here the potential coil or the moving coil is connected at, which is connected, C connection or MC connection. So the potential coil or the moving coil is connected at the mains. Yes or not? The potential coil or the moving coil is connected at the mains. So in this connection, what you understand? So moving coil is connected to mains. Moving coil is connected to mains. Next, another way of connecting is our current coil, load, and now the potential coil or the moving coil our is resistor, and this is connected here. Connected here. So we can take this as current coil or the moving coil, we can say. I will write moving coil because you can confuse here. I will write this as moving coil. Moving coil. This is our supply. Now if you check what is happening here, this MC moving coil is connected at what side? At load side. This is connected at main side, this is connected to load side. So what we can call now here is the moving coil is connected main side, so this is called as MC connection. What do we call this as? Call it as MC connection. Whereas we call this as LC connection. Call this as LC. So now if you see the MC connection, what is going to happen? Let me write here. In MC connection, what is going to happen? In MC connection, what is the true value of the power and what is the measured value of the power if you check? So the measured value is always this, right? Actually the true value is this. So this is a true value, right? This is a true value. Always the load across whatever the power consumed, that is a true value na? The true. Okay. So the true value we can take it as VL cos phi, that everybody knows. Okay. So what is the true value of the power? That we can take it as VL cos phi. But if we check the measurement value, what is going to happen? There the terminals are here, right? So with respect to this, if we check now, it is including this current coil also na? Yes or not? So let me draw with a different color. It is including the current coil also, my dear. Current coil also. So as it is including current coil, so the power will be here. Power consumed by the current coil plus the true value. Power consumed by the current coil is nothing but current passing to the current coil and resistance of the current coil plus the true. Definitely there is an error. Yes or not? So this is one of the important points that you have to understand in our MC connection. So what is the error here? The error is nothing but measurement value minus true value. If you take, is the true value. So this is a true value, this is a measurement value. So if you take the error, what is the error? Measurement value minus that is the error is equal to I square R. Okay. So in MC connection, the error is due to what? The current coil. In MC connection, do you understand? This is a connection error. When you connect that particular moving coil at the front or at the back of the current coil, we are going to have an extra term. Okay. So in MC connection, error is due to which coil? Let us take one more case now. The second case, that is LC connection. We go for LC connection. LC connection means what? The moving coil is connected at the load side. So here also the true value is what? The true value is VL IL cos phi, but the measurement value is what, dear? Check. We check. So this is a true value, but the measurement value is what? This power to this na. So this power and this power, this total. Yes or not? So power consumed by the potential coil and also the load. So power consumed by the potential coil plus the true value or the load. What is the power consumed by the potential coil? Power is equal to voltage into I. So that is nothing but what? Voltage into I. I is equal to V by PC. We can write. Yes or not? So this is V square potential coil by resistance of the potential coil. Resistance of the potential coil we can take. Yes or not? Power is equal to V into I na. I is equal to V by R na. So V square by R plus is a true value. What is the true value? That is the load power. So now the measurement value is again having an error. The measurement value is having again an error compared. Okay. So here the error is due to what? Here the error is due to potential coil. The potential. So therefore I can write in LC the error is due to LC connection. The error is due to potential coil. Have you observed, or the moving coil due to potential coil or the moving coil? Try to understand based upon the connection you are going to get. So one important point I want to tell you here, the errors are expected question. These errors are expected questions, my dear. Errors are expected. Whether it is a LC connection or MC connection, always remember the error is offered. Whether it is a LC connection or MC connection, always remember the error is offered due to what? Due to the coil which is connected to the load side. If you see the MC connection, in the MC connection, the current coil is connected to the load side. That's why the error is due to the current coil. Whereas in LC connection, the moving coil is connected to the load side. So that's why it is due to moving coil. You understand? So if you want to reduce the error here, if I want to reduce the error, what does it mean? The current passing through the current coil must be less. Current passing through the current coil must be less means, this current coil passing current coil must be less means, it should be what? It should be what? High load. When a high load are there, then definitely current passing through the current coil will be less. You understand? You understand? Small current is possible at a high loads. Similarly, if you want to reduce this particular error, this VPC must be less. VPC must be less means what? Obviously the current passing through the load must be more, current passing through this RSC must be less. Current passing through the load must be high means that should be low loads. Okay na? Low loads will allow higher currents. So please make a note of this. This is eliminated, or this is best suitable for the small currents or high loads. This is best suitable for high currents or low loads. So that is a quotation you can write. Okay. So this is one of the important area where you are going to get the questions. Error due to the connections. error due to the connection. This is one of the important area, error due to the connection. Now let us move. By using this particular dynamometer or wattmeter, we can measure the three-phase power. To measure the three-phase power, we are using one concept called Blondel's theorem. In Blondel's theorem, we are using the 2 wattmeter method. So how the 2 wattmeter method is best suitable to measure the three-phase power, that we'll see upcoming lecture. Thank you.